Okay, if you're not able to unmute and talk, you can also type in. Yeah, thanks, Saurav. So please type in your answer or speak up. Okay, whenever possible, speak up. Okay, so let's start today's session, and we are going to see the difference between these two conditions to start off. So when can we say a flow is irrotational, and when can we say flow is incompressible? You can type in your answers. So we saw the condition of incompressibility earlier also, right? Yes, anyone? And if you don't know, just say you don't know, so that I don't keep waiting for your answer. Okay. Yeah, so we say that flow is incompressible when it satisfies the condition that divergence of rho v is equal to 0, and assuming that density is not changing, it's a homogeneous fluid, we can also say del dot v is equal to 0. So this is the condition of incompressibility, and using this, in fact, we defined something called the stream function psi. So what are the properties of stream function? Okay, one property we saw is that the tangent to psi gives the direction of velocity, right? So this is the definition of streamline. So if I take the tangent to psi, it gives the direction of velocity. At that point, wherever you are taking the tangent. Okay, and the properties of psi is that you can obtain the velocity field. Velocity field, let's say we are talking about the two-dimensional flow. So we have u comma v. So in 2 dimensions, we can define u is dou psi by dou y, and v is minus dou psi by dou x, and this we have seen in the previous tutorials and in the previous week lectures. Okay. Now coming to the condition of irrotationality. So what is rotational flow? Rotational is when there is some sort of movement of fluid particles with respect to each other, right? So for example, let's say there is a flow like this in a channel. Okay, so there is a flow in a channel. The velocity very close to the wall will be 0. Okay, the velocity here will be 0, and here it will be very high. So in fact, if you draw the velocity profile along the channel, it turns out to be like this. Now if I look at any two layers, so one layer is moving with very high velocity, the next layer is moving with slightly lesser velocity. So with comparison to both of these, if I sit along this fluid particle, which is, let's say, moving with v velocity, this fluid particle is actually moving with v plus dv. So if I was sitting here, with respect to this, there is a relative motion. And if this relative motion of fluid particles is rotational, it creates something called eddies, right? So there can be vortices, there can be eddies, and they have very high localized vorticity. Okay, so first, can you tell me, if there is a vortex, we know there is high vorticity. But if I tell you that there is high vorticity, does it necessarily imply that there will be vortices in the flow? Yeah, you can type in your answers if you don't want to unmute. So my question is, let's say there is a flow. Let's say a flow has high vorticity. So if a flow has high vorticity, does it necessarily mean that there will be vortices? It's a yes or no answer. Come on. Yes? Okay, why do you think so? Because there is high vorticity. Okay, can you tell me, can you tell me what is the definition of vorticity? At any location, vorticity is defined as? Curl of V, right? Have you seen this equation? Now if curl of V is non-zero, it does not mean that there will be vortices. So let's go back to the example we were looking at. In this case, there is differential motion of the fluid particle. So at this instant, actually, this top particle and the bottom particle, they are rotating with respect to each other. So there is very high vorticity in shear flows. This is a shear flow. So this is as an example where there is shear between two layers. And when there is shear, that is, there is differential motion between different fluid particles, there will be some rotational effects. There is going to be a high vorticity, because what are you doing? You are basically sitting at one point when you calculate curl of V. Okay, so let's say in any field, change a color over here. Okay, so in a flow field, I can define the velocity at, and I'm going to consider 2 dimensions only. So I can define it at any location at any given time. Okay. Now let me fix time. So let's fix time at t0. And at this time, I am basically calculating this curl of V. So curl of V can be calculated at different locations x and y. So this curl of V is basically omega, and this will also be a function of x comma y. What is curl of V? How do we calculate it? So the formula is simply, you have to do this calculation of determinant, dou by dou x, dou by dou y, dou by dou z. Velocity is u, v and w. Now assuming that this is 0, we only have the k component. In the k component you have dou v by dou x minus dou u by dou y. Now if this is the vorticity at some location, and I have this case which we took, this is a flow particle which is moving at velocity v, there is another flow particle which is moving at velocity v plus dv. Right, so there is x component. Okay, I should write, because this is x motion, let me write it as u so that it's clearer. Right, so here there is velocity u and the y velocity is, let's say, 0. Okay, and here the velocity is u plus du and y velocity is again 0. So now tell me, what is the vorticity? V component is not there, so this term becomes 0. So we have a minus k cap dou u by dou y, which means in the y direction, so this is y cap direction, this is x cap direction. So in the y direction, is there a change in the u component? Yes, there is a change of du amount. So dou u by dou y is non-zero, which means vorticity is non-zero in this case. But actually the flow was only from left to right. Did you understand this? So the vorticity is non-zero in a shear flow, which need not have vortices. Okay, so the first important thing for today that we should remember is that there is a difference between vorticity and vortices. Okay, so this is the discussion we've had. If there are vortices, we know there is fluid rotation, right? So vortices means there is some rotation in a particular location, and hence because of the rotational energy, because of this rotational flow, the vorticity is going to be high. It is going to be localized, it is going to be high. But if the vorticity is high, does not imply that there are vortices. Vorticity can be non-zero even in shear flows where there are no vortices. Okay, so this is the first most important thing we'll remember. Now, what is an irrotational flow? Coming back to the original question. Vorticity is 0. Yeah, vorticity is 0 at every location, right? So vorticity, which we have defined as curl of velocity, it is 0 at for all x comma y, right? Okay, so under this condition we can define some very special function. So let's go back and see what curl of v meant. Curl of v meant that dou v by dou x minus dou u by dou y is 0. And if you took all the three components, you can actually write that. So let's write this again over here. Dou v by dou x minus dou u by dou y, and the other components would be, so if you take the j component, it's dou w by dou x minus dou u by dou z, and the last component is I component is dou w by dou x minus dou v by dou z, right? So these are the three components, and each component should be equal to 0. That is when the vorticity will be 0. So now we can actually define some special function. So we define that velocity is equal to minus gradient of phi. Okay. What happens if we do this? So velocity is gradient of phi basically gives me, if I just take minus velocity here, dou by dou x of phi I cap plus dou by dou y of phi in j cap plus dou phi by dou z in k cap. But what are these components actually? So you can see that u, v and w are the components of velocity. So now you can relate u is equal to minus dou phi by dou x and so on, right? V is dou phi by minus dou phi by dou y, and w is minus dou phi by dou z. Okay, do you know what this negative sign means? I mean, anyways, I am defining this, right? It is a construct of our definition. So why do you think we put a negative sign? See, whenever some theory is given to you, you should always raise questions. You should ask why is it like this and not the other way around. We could have simply said velocity is grad phi. Why did we add a negative sign over here? Any idea? Achha, okay, so have two bodies A and B, and I tell you that temperature of A is greater than the temperature of B. This is the information, and they are connected. So heat will transfer from A to B or B to A. Yes, in which direction? Yeah, A to B. Okay, it's very obvious. Yeah. So heat transfer is A to B. So if I ask you A to B, what was dt? So when we write dt, it is always the final minus the initial. So the final state was Tb, and the final location where it is going to. So this is the final and this is the initial, right? So Tb minus Ta. This is actually negative. So it is obvious to us that heat transfer happens in direction of decreasing temperature potential. Similarly, now if you look at your velocity potential, the way it is defined, so if this is your flow, so there's some flow over here. If you look at this location phi and this location phi 1 and phi 2, you know that velocity is flowing in this direction, right? If velocity is flowing in this direction, then by the analogy to this heat transfer problem, we would like to imagine that potential is actually decreasing. So there is transfer of heat from high temperature to low temperature. There is transfer from there's flow always from high pressure area to low pressure area, right? So similarly, I would like to say that there is a flow from high potential to low potential. Okay, so this is how I would like to imagine it, or how most fluid mechanists would like to imagine it. And hence in many books you will see that because we want to imagine there is flow from high to low potential, we put this negative sign. So we say that phi 2 should be lesser than phi 1. So it should be d phi, negative of d phi will define the direction of velocity, defines positive flow direction. Hence we have the negative sign. Okay, so that's why we say velocity is minus grad phi. Alright, now going back to the main thing. So we started by saying we have an irrotational flow and we define velocity to be minus grad phi. Why? Because if I look at this minus grad phi, this particular condition, if I put it back in the curl, so I want the curl of velocity to be 0, and I have now defined velocity to be gradient of some function. So if I take this curl of grad phi with a negative sign, it is automatically 0 because grad of curl, curl of grad, not grad of curl. So this is a property, it's a mathematical property that curl of grad of a function is 0. So this is a well-known property. In fact, you can very easily prove it. So if you take the gradient of phi, which we have already written above, and what I'll do is I'll write it in a notation, dou phi by dou xi. So xi means that there is so dou x, dou y, dou z. So I goes from 1 to 3. So this is dou phi by dou xi in the xi cap direction. And then you can also apply the curl to this grad phi. And in this particular notation, which is also called the Einstein notation, see, you can explicitly put this function this equation, you can plug it back into the gradient, the curl that we evaluated over here, and you can get the same result. But I am showing you how to get this with Einstein notation. So if you take curl of grad, in fact if you take curl of anything, curl of any vector, the way to write it is epsilon ijk dou by dou xj and the k component of A. So you can see what this means is, if I look at the dou by dou x, dou by dou y, dou by dou z, okay, and then you have ax, ay, az. These are the components I, j, k. So let's take, for example, the first component. So first component is the ith component. What it means is dou by dou y of az minus dou by dou z of ay. So here y is the second component, z is the third component, I is the first component, right? So first component, that's 1. So we'll say epsilon 1, and we are talking about y, which is 2 and 3. Epsilon 1, 2, 3, and this is dou x3, dou a3, the third component of A, dou a3 by dou x2, plus, now if I look at this component, what is it? It is dou by dou x3, so z is x3 and ay is a2. So now it is epsilon I is still the first component, but now the 2 and 3 indices are exchanged. So this is 3, 2. So the property of this epsilon is that epsilon ijk, if I and j and k are not equal, and if they are cyclic, cyclic means 1, 2, 3 or 2, 3, 1. So it has to be 1, 2, 3. If you have any doubts in this notation, you can stop me. This is used quite a lot in fluid mechanics and mathematics. So it's helpful to know this. So if it is cyclic like this, if it is 1, 2, 3 or it's 3, 1, 2 or 2, 3, 1, so these are cyclic combinations. If there is a cyclic combination, then epsilon ijk will be 1. Okay. But if epsilon ijk is taken and we have any other combination which is not cyclic and ijk are not equal, okay, so ijk not equal and not cyclic, then the notation is this is minus 1, okay, and in any other condition epsilon ijk is 0. Any other condition being, if it is, let's say 1, 2, 2, 1, 3, 1, so if any index is repeated, then the value is 0. So these are the properties of epsilon ijk. So now we can write curl of A as in this form. So I am going to do that here. Epsilon ijk dou by dou xj into the kth component of whatever is in my brackets over here, right? So the kth component over here is dou by dou xk of phi, right? I hope you guys are following this. So now if you evaluate this, there is dou by dou xj, dou by dou xk. We can immediately remove all the terms where ijk are repeated. So we have to take only the non-repeating cases. And what you will see is, let's say if I take epsilon 1, 2, 3, so that is 1 multiplied to dou by dou x2, dou by dou x3 of phi. And now take epsilon 1, 3, 2, that will be minus 1 dou by dou x3, dou by dou x2 of phi. So these two terms, they cancel out. Okay, right? So there are several terms actually. I'm just showing you any one term, and the reason why I went for this Einstein notation is because it becomes quite easy to see what is happening. If you put this function here in this notation, then it will become quite complicated to evaluate it, right? So that's why I've used the Einstein notation, and you can see that all the terms, the cyclic and non-cyclic terms, will cancel each other out, and as a result you will find that curl of grad phi is actually 0. So this is often asked as a proof in fundamental courses. Okay, so now that we agree that in case of irrotational flows we can define the velocity field with this function, let's talk more about this function. Yeah, so this function phi is called a potential function. Okay, or it is also called a potential velocity function. And like we were discussing about two-dimensional flows. So in two-dimensional flows, what happens is you have just the u and v component, and you have defined velocity to be minus grad phi. So u is equal to minus dou phi by dou x, and v is equal to minus dou phi by dou y. Now if you remember, we just discussed the stream function also, and the stream function was defined like this: u is equal to dou psi by dou y, and v is equal to dou psi by dou x with a negative sign, right? Yeah. Yeah, so you see, if I'm looking at the x component, phi will be differentiated by x, but psi will be differentiated with the other component y. So this is how phi and psi are related, and we can go ahead and derive a relation between phi and psi, which is quite simple. So we know that tangent, see, there is a stream function psi, and we know that the tangent to this at any location x comma y, it gives me the velocity vector, right? And that is how we obtained this, in fact. So if I write the tangent slope, so let's write the slope of tangent to psi. So how do we define that? That's nothing but dy by dx, right? So dy by dx at a point where I hold psi constant. So psi is constant. For that I can just take these functions, see, dou psi by dou y and dou psi by dou x. So I'm going to take dou psi by dou y divided by dou psi by dou x with a no, so that's it, positive, and this gives me dou psi by dou y is u, and dou psi by dou x is minus of v. Okay, so the slope of tangent to psi is minus u by v at any location. Now at the same location I can also take this potential function, right? There may be some potential function, I don't know how it looks, but there is some function phi, and I can define a tangent to this at this point, and we can now define the slope. So slope of tangent to phi, is there a question? Okay, so the slope of tangent to phi can be calculated again. You take dy by dx, but this time we hold phi as constant. So what that means is I cannot use dou psi condition, but I can use the dou phi condition, right? And see, when you write like this gets cancelled, these terms are able to cancel because psi was constant, right? So when I hold phi as constant, I can now define dou phi by dou y divided by dou phi by dou x. And what is dou phi by dou y? Minus of v. Dou phi by dou x is minus of u. So this is v by u. So if I take the slope of psi as m1 and I take this slope as m2, you can immediately see m1 into m2 is, if you multiply m1 into m2, it is minus 1. What is this condition of? So this you would have studied in your basic math courses, geometry. This is a condition for anyone? If there are two functions and the slope, the tangent slope of these two functions is related like this, m1 m2 is equal to minus 1. Yeah, does anyone have any idea? Pradeep, Ketan? Okay. You can look this up. So you must have actually seen this in basic math. When there are two parallel lines, there are certain conditions. When there are two perpendicular lines, there are, yeah? No, so what is the condition for two lines to be perpendicular? See, the slope of this is m1 and the slope of this is m2. If it is parallel, m1 and m2 will be equal, right? m1 is equal to m2, that gives the condition for parallel. And if m1 into m2 is minus 1, that gives the condition for perpendicular lines. So here we are taking the tangents to the function. So this is perpendicular slopes, I will say, which means that psi and phi are perpendicular to each other. So I am going to show you some examples where we will draw the stream function and we will draw the potential function, and you will see that they are always perpendicular to each other. Okay, apart from this, there is a very nice condition that is satisfied by both psi and phi. So let me discuss that. Okay, we saw that there is irrotational flow. If there is an irrotational flow, we have already defined the condition is curl of v is 0, and we wrote the two-dimensional version of this is dou v by dou x, right? Yeah, dou v by dou x minus dou u by dou y is equal to 0. And if we have incompressible flow, incompressible flow. Yeah, so then we have del dot v is 0, and this in 2D gives me the condition that dou u by dou x plus dou v by dou y is 0. Now if I combine both the conditions, let's say I have a flow where both of these conditions are true, that is del dot v is also 0 and curl of v is also 0. So then I can define both psi and phi. Remember, if a flow is irrotational, define phi. If a flow is incompressible, define psi. But if you can define psi, does not mean that you can define phi, because an incompressible flow can have rotational features. We just saw the example of shear flow, right? But if you have an irrotational flow, it does not necessarily imply that the flow is incompressible. But if I say that both the cases, both the conditions can be assumed, let's say both the conditions are true, this is if, then psi and phi both can be defined. Okay, and now I will use the irrotational condition, and I'll put v and u in terms of the incompressible condition. So this is simple. Because there is incompressibility, I can define u as minus dou psi by plus dou psi by dou y, and v as minus dou psi by dou x. This is by, so let me call this condition 1, condition 2. So this is by condition 2, and I'm going to put it in condition 1, which is for irrotationality. So dou v by dou y minus dou u by dou x is equal to what? So dou v by dou y, if I do this, I'll put v here, minus dou psi by dou x minus dou by dou x of u, which is dou psi by dou y. Right? So if you evaluate this, what do you get? You get dou square psi by dou x square plus dou square psi by dou y square, the whole with a negative sign, is equal to 0. Okay, so what this gives me is the Laplacian of psi is 0. Now you can do the opposite. Let's start from condition 1. Condition 1 is irrotational. So if we have irrotational flow, u is minus dou phi by dou x and v is minus dou phi by dou y, and you put this in condition number 2, which is the condition for incompressibility. So I should have dou u by dou x plus dou v by dou y is 0. So if you do this now, you can see dou square phi by dou x square plus dou square phi by dou y square is 0. So again, the Laplacian of phi is also 0. So this del square operator, which is nothing but this dou square by dou x square, dou square by dou y square, this is an operator called Laplacian, and the Laplacian operator will when operated on phi and psi will give 0. But this is only if we can assume both irrotational and incompressible conditions. Any questions still here? Are there any questions still here? No? Yeah. Okay. Okay, so let us solve a question now. So we have a flow field. So consider a flow field. Such that the velocity, the stream function psi is given to you. Psi is equal to ax square minus ay square, and a is also given, which is 3 second inverse. So you have to check whether this flow is irrotational. Okay, so is the flow irrotational? See, first thing is, since you have defined psi, obviously it is incompressible, and you can apply the condition of incompressibility and check immediately. Dou u by dou x will be 2ax, and dou v by you can define u and v from psi, and you can check del dot v, and it will turn out to be 0. But what you have to check is, first you define from psi, you define u and v, and then check is curl of v equal to 0. Okay, and if it is irrotational, then define phi. Okay, so first let me wait for you to check this. Just try on your own. Is it irrotational or not? Yeah, so are you guys trying? See, one way to do is, you know psi, so let's define u and v. What do you get as u? U is dou psi by dou y. Yes? Yeah, anyone? Okay, you just have to differentiate this function. So dou psi by dou y turns out to be minus 2ay, and minus dou psi by dou x is minus of 2ax, right? Now to check for irrotationality, what we need to do is, we need to ask if curl of v is 0. So curl of v is dou v by dou x minus dou u by dou y. So dou by dou x of v, which is minus 2ax, minus dou by dou y of u, which is minus 2ay. So this is minus 2a minus of minus 2a. So indeed it is 0. Yes, the flow is irrotational. Now there is another method to check this. So we just now saw that if a flow is both irrotational and incompressible, then psi, when operated by a Laplacian, will give 0. Right? So I know the stream function psi. So all I need to do is just check if del square psi is 0. Right? If it is 0, then the flow can be assumed to be irrotational. I mean, not assumed to be, it is irrotational. Okay, so we can do this dou square by dou x square plus dou square by dou y square operated on psi, and psi was ax square minus ay square. So it is dou square by dou x square plus dou square by dou y square So dou square by dou x square of ax square minus ay square, and similarly dou square by dou y square of ax square minus ay square. So the first term, it gives me 2a, and if I differentiate 2 times with y over here, it gives me minus 2a. So this also turns out to be 0. So since del square psi is 0, it must be true that the flow is irrotational. Now what we need to do is, we need to define the potential function phi. So how to define phi? Okay, I think you guys should try and answer at least something. So I'm going to wait for an answer now. You know psi, you have found the velocity field. How do we find phi? Yes guys, how do we find phi? If you know the velocity field, how do we define a potential function? Okay, this is quite a simple question. Please answer, and if you don't know, please say you don't know. You can type in your answers. Okay. Alright, so how do we define phi? We know, first of all, how did we define it in the starting? We said that curl of V is 0. Hence, I can define velocity as minus gradient of some function phi. And for a two-dimensional flow, we saw that u is equal to minus dou phi by dou x, and v is equal to minus dou phi by dou y, right? And you just now found u and v. So if I know that u is equal to what was u? Minus 2ay. Okay, so minus 2ay, and I know this is equal to minus dou phi by dou x. So now how do we find phi? We just have to integrate this. Similarly, you can also use the v equation, which is, so v was minus 2ax, and this is nothing but minus dou phi by dou y. So you just have to integrate with respect to y. So you know how to do partial integration, right? Because this is going to be 2ay into x integral is equal to dou phi integral. So phi, sorry, I missed dx. So this is dou x. So since the integral is with respect to x, we can hold y as a constant. So phi is equal to 2ay x plus some function of y. Remember, if you have, let's say if you had x dx and you were integrating this, what would you do? You will say x square plus constant directly. But now we have y dou x integral. So this has to be yx plus some constant. But this constant is only with respect to the differential of x. It can still be a function of y. So that is why we don't write constant, and instead we write function of y. I hope this is clear. Okay. So this is a rough, so I will move this. So when I integrate from u, okay, so I am talking about partial integration. Okay, so this is partial integration, right? What is partial integration? Okay, let me give you two functions. f1, let's say f1 is 2a, let's take a simple example. Let's say xy plus y square, and I have another function f2 which is xy plus 3 plus 3y. I don't know, it can be anything. Now if I ask you what is dou f1 by dou x, what is dou f1 by dou x? Yeah, just do the partial differential and tell me. Yeah. we are doing differential dou f1 by dou x. So differentiate xy with respect to x. What is it? Y, that's it. Yeah, plus 0, that's it. And what about dou f2 by dou x? Y plus 0, y. Okay. So now you see, if I did partial differential with respect to x for f1 or for f2, it doesn't matter, I'm getting the same answer. So in fact, if I integrate now, so if I integrate, f is equal to y dou x integral. So I can say for sure that in this term y into x is present. But the next term, it can be either y square, it can be 3y, it can be a constant, let's say 7, it can be anything, right? So there has to be some function g of y, because when I do dou f by dou x, I will just get y plus dou by dou x of gy, which is 0. Okay, so this is the general assumption. It can be any function with respect to y. So this is the generalized solution of this partial integration, and that's what I have written over here. So you will, when you do this partial integration, you are doing it with respect to x. So here it can be any function of y, right? Similarly, because I integrated with respect to x, but now I am going to use this equation, and what do I get? I get 2ax dou y is equal to dou phi integral. Now I am going to integrate partially with respect to y. So this is going to give 2ayx. Again the same thing, but because I am integrating with respect to y, there can be any generalized function g of x, and this is phi. So if you just solve with respect to u, you cannot be sure what is the potential function. That is why you have to solve with u and with v. And now that you got phi in these terms, and you know it is the same phi, it is the same potential function, if you compare, you can say that this is a function of y, this is a function of x. They have to be equal, because ultimately the potential function is the same, right? So it is 2axy plus f of y is equal to 2axy plus g of x. How is this possible? A function of y and a function of x both are equal. When is this possible? Only if they both are constants. Both are same, both are constant. There is no dependence on x or y. Okay, so phi is nothing but 2axy plus constant. So you cannot directly write constant when you are integrating partially. You have to first write function of y. Here get the same answer, you get it, you get a g of x, and then when you compare the functional forms, you realize that there is a function of y and a function of x, and they have to be equated. This is not possible until and unless both of them are constant and the same constant. So this is my potential function. Okay. Any questions here? No. Okay, so let's move forward, and now we are going to look at some elementary flows. So what I mean by elementary flows is these are some flows that you will encounter, and most of the questions will come from these type of flows, and these are some idealized imagined flows. And I'll also tell you why they are elementary and what it means for us when we are solving some complex flows. Then we can take a combination of these elementary flows. So let us start with something very simple, which is called a source. Okay, even before that, let's start with uniform flow. uniform flow is basically, you can imagine that there's just flow like this, and the velocity is u at all points. So u at all points, velocity at each point is just u comma 0. It is constant at all points. This is uniform flow. So now that you know this velocity, can you define what is psi and phi? See, I've already defined the velocity field for you. So the u component is some u naught, let's say I'll call it u naught, and v is 0. So what is psi? So I'm not going to write the equation again and again. We know u is minus, u is dou psi by dou x, and u is also minus dou phi by dou x. U is dou psi by dou y and minus dou phi by dou x. Yeah, so from this equation, can you tell me what is psi? I'm going to wait for an answer. This is a simple integration. See, u is u naught. Take dou y on the other side, integrate, and tell me what is psi. And similarly, tell me what is phi. You can also type your answers. And I have many examples to go through. What is the integration here? What does this give? U naught y, yeah. So this, yeah. And what about phi? U naught is minus dou phi by dou x. So what is phi? Minus u naught x. Okay, so this is, oh, this is a minus, no? Okay, so this is the psi and phi. So let us plot the psi and phi functions. So let me use, let's use blue color for psi. Okay. U naught y. So when psi is constant, then y is constant and x can vary. Okay. So imagine you have your xy plane. This is a rough. If I hold y is constant and x can vary, it gives me horizontal lines, right? So psi is going to be horizontal lines. So this is like psi 1, psi 2, psi 3, and you can now see that, remember we said when I have a streamline, then the tangent to that streamline is the velocity direction, and I started with a flow where the velocity is in the x direction. These are the streamlines. Tangent to these line is the line itself. So this is the velocity direction, right? This is the velocity direction. Okay, so these are the streamlines. Now what about phi? If I hold phi as constant, that means x is held constant. So x is fixed, but y can vary. So that gives me vertical lines. So I'm going to draw, let's say with orange here. So this is phi 1, phi 2, and so on. Okay. And also we saw this property that psi and phi are perpendicular to each other. So horizontal and vertical lines, they are indeed perpendicular to each other. So all these conditions that we saw are being satisfied over here. Okay, so these are the potential functions, and we also said that the flow is from higher potential to lower potential. So you can say that phi 1 is higher than phi 2, and hence the flow is in this direction. Are there any questions about uniform flow? Because we are going to go to some more imaginative flows. Yeah, so you might want to note that psi and phi are perpendicular to each other. The other property that we knew is tangent to psi gives velocity direction. Okay, so if there are no questions over here, let's go to the second example. Which is source or sink type of flow. So what a source or sink flow means is, let's say I have a point here and it's just throwing out flow. You can imagine you're holding a pipe and it's just throwing flow in the plane. So there is flow radially in all directions. Okay. So this is our imagination. I am imagining that this is the kind of flow we have. And let's say sink means what? That flow from everywhere is going radially into this point and disappearing. Okay, so there's like a suction over here and everything is being sucked into this sink point. So this is source and sink. So I'll just solve for source. Now here the velocity will be defined in, see, velocity is radially outwards. So we are going to use the cylindrical coordinates. Which are r and theta. So r cap and theta cap. Now in the r cap direction the velocity is constant, right? So I'm going to say that there is a velocity Vr which is I can say some constant q by 2 pi r. So as the flow moves from, let's say, this smaller radius to a larger radius, the velocity is decaying. That is why there is this Vr is dependent on 1 by r. And V theta, so in this flow what do you think is V theta? The flow is only radial, it is not having any tangential direction. Tangential direction would be like this. That type of flow is not there. Okay, so V theta is 0. So now let us define psi. So what is psi and what is phi? So in the cylindrical coordinates we have actually seen the definitions. So for example, for psi we know Vr is equal to 1 by r dou psi by dou theta, and V theta is equal to minus dou psi by dou r. So this is the equation. And for phi also we know in the cylindrical coordinates Vr is equal to minus dou phi by dou r, and V theta is equal to minus dou phi by dou theta and 1 by r is there. Yeah, so these are the definitions of psi and phi, and we are going to use this and integrate given this velocity field of a radial flow. Let's see what we get. So we have q by 2 pi r is equal to 1 by r dou psi by dou theta. So if you cancel out r, you get q dou theta by 2 pi integral is dou psi integral, right? So this is q theta by 2 pi, and of course you'll have a function of r, remember the partial integral, but since v theta is 0, you'll find that dou psi by dou r just gives a constant, so this will be a constant. Okay, so I'm just directly going to say this is a constant, but always remember that you have to do a partial integration and check with the other velocity component. Okay. So this is psi. Now similarly I can also find phi. So q by 2 pi r is minus dou phi by dou r. So if you integrate this, what do you get? Q by 2 pi, I'll take it outside, dou r by r integral minus sign dou phi integral. Okay. And on the other hand, you'll have dou phi by dou theta is 0. So the only contribution is this r. So we get phi is equal to minus q by 2 pi. What is the integral of dou r by r? Are you guys following? Okay, so dou r by r integral, this is something standard you would know. It is log r. So this is the potential function, and we have also defined the stream function. So now you can imagine, let me draw the velocity field. Velocity field is like this. So there is a source. The velocity is high when we are close to the source. As we go far, the velocity becomes smaller. So I am drawing smaller velocity vectors, right? My velocity field, and let us draw the stream functions. So the stream functions are when psi is constant. Psi is constant means theta is held constant and r can vary, right? So if psi is constant, then theta is fixed and r can vary. So these are basically the radial lines. So it is in fact these lines which you should have guessed, because velocity is tangent to the stream function. So this is psi. Similarly, this is psi. Oh, there's no arrow. Sorry. Okay. So this is psi. What about phi? So if I hold phi as constant, what that gives me is log of r is constant, which is nothing but r is constant, because e to the power constant is also a constant. So now you have to hold r constant. Which is basically a circle. Okay, so these circles of constant radius, these are my potential functions. And again you can see, sorry about that. So again you can see that at any point over here, this is psi and this is phi, and psi and phi are perpendicular to each other, right? Because a radial line cutting across a circle is perpendicular to it. Any questions? Okay, so I'll leave the sink case for you. So you have to now imagine velocity is inwards, and in that case VR will be not positive but it will be negative, so minus q by 2 pi r. Okay, the only thing that will change is, see, if I write phi 1 so the only thing that changes is how you define your phi. So this is phi 1, phi 2 and so on, and phi is decreasing as we move away from this dot. But in sync what will happen, it will be just the opposite picture. The flow is into this point, so the stream functions are still going to be all radial. Okay, these are the stream functions, and these are again this potential function phi is again going to be circles, but the change will be the potential function will be higher on the outside circle as compared to the inside circle. So as you move away from the center, phi is going to actually increase. In this case, in the case of a source, phi is decreasing as you move out, because remember we said high to low potential there is a flow. In source the flow is outwards, so phi is decreasing outwards. In sync the flow is inwards, so phi is decreasing inwards. I hope this part is clear. Yeah, at the center. Yes, so yeah, it is. So here temperature should decrease or potential should decrease as we go to the center in case of a sink. In case of source, this will be very high temperature. That's why it is dissipating heat. So this is very high potential, and as you move out, it will the potential will decrease. It is the same analogy with temperature. Okay, yeah. No, this is not an assumption. I mean, the flow is an assumption. You cannot have a source or a sink, because see, at the center there is a singularity because the way you have defined your velocity, it is q by 2 pi r. At r equal to 0 this becomes infinity. That is not well defined. Okay, so in that sense it is not real. Yeah. In the case of sink, there is no, in this flow that we have assumed, there is no vortex. Where is a vortex? These are potential flow lines. Don't confuse this with vortex. The next flow that we will discuss is a vortex. Okay. Now, is this part clear, by the way, source and sink? Yeah? Okay, so let's talk about vortex. But we are talking about irrotational flows. So can we define a vortex in an irrotational flow? Can we define a vortex in an irrotational flow? Basically my questions. What? No, vorticity will be 0. See, this is what we started the class with this. There is a difference between vorticity and vortices. If you have vortices, you should understand the localized regions where there is this rotational flow. The vorticity will be there. If there is vorticity, it is not necessary there will be vortices, right? For example, we saw this shear flow where one layer is moving with respect to another. So there is some movement with respect to another. So there is a gradient. There is going to be a curl of V, which is non-zero. So there can be rotational flow, there can be vorticity, but there need not be vortices. Now my question is, we are talking about incompressible irrotational flow. So can I define an irrotational vortex? The answer is yes, as long as I ensure that the overall this curl of V equal to 0 condition is satisfied. Okay, so how do we do that? So let's see. First, let's imagine an irrotational vortex, and we'll also see why this is unrealistic. Okay, because if there is a vortex, vorticity should be there. Okay, so we have to ensure that curl of V is 0, and we have to ensure that del dot V is 0, and we have to imagine a vortex. So vortex means there is flow in this direction, in the theta direction, right? Till now we saw flow in the radial direction, but now there should not be radial flow, there should be tangential flow. So I'm going to draw the velocity field now. So let's imagine there is some flow in this circular manner. There is a flow. So at this point, this is the direction of velocity. At this point, this is the direction. At this point, this is the direction. At this point, this is the direction, and so on, right? So I can draw this more carefully. Okay, so this is how the velocity field looks at one point, and as I go closer to the center, velocity vectors are increasing. As I go far away, the velocity vectors are decreasing, which means it's a flow where as you move away from the center, the strength of this circulation, the strength of the velocity decreases. Okay, so there's no radial flow. This is how I am imagining the flow. So VR is 0, and V theta is like we said, it is constant in one circle, so the strength remains same along this circle, but as I move away from this circle, the strength decreases. So with respect to theta, it is a constant, so let me say q by 2 pi, but as r increases, V theta should decrease, so I am going to write r in the denominator. So you can see as r increases, V theta decreases. And you can immediately see that when VR was q by 2 pi r, then we had the source flow. Now I have just exchanged these two things, and now we have a rotational flow. We have an irrotational vortex. Alright. Now if the condition of irrotationality is to be satisfied, then how do we define psi and phi? So let's start with VR. VR is 0, which is nothing but, so let me take these equations from here. Okay, so VR is 0, but it is also 1 by r dou psi by dou theta, and it is also minus dou phi by dou r. On the other hand, I have v theta, which is q by 2 pi r, and this is equal to minus, yes, I have to look at this equation. V theta is minus dou psi by dou r and minus 1 by r dou phi by dou theta. So we can integrate again. Let's do this integration. So psi is nothing but minus q by 2 pi dou r by r integral. We just now saw this is log. So minus q by 2 pi log r plus some function of theta, but as you can see from here, psi is not dependent on theta, so I'm just going to write a constant. Similarly, I can define phi. So if I integrate this equation, I have to take r will get cancelled, so I have minus q by 2 pi dou theta integral, right? So this is minus q by 2 pi theta plus some constant, again because phi, if you see, dou phi by dou r is 0, so there is no dependence on r. Is this okay? Is this part clear? So we have simply integrated the equations, and we have satisfied the condition that curl of v is 0, which means I am able to define phi. So I can define phi only when curl of v is 0, right? And this is the velocity field. So now if you see, what is psi? Psi is this function, and a constant psi, a streamline, will be defined when radius is held constant, which is circles. So circles are now the streamlines. Okay, they are supposed to be concentric circles, excuse my drawing, but yeah, so this is these are the stream functions psi, and now you can draw the potential functions. So how does the potential function look? If phi is constant, theta is constant. Theta constant means r can vary. So this is how you have phi. Okay, so I'm going to label, let's call this phi x, and let's call this phi y. Can you tell me which one is greater? Phi x is greater or phi y is greater? Yeah, by our definition, velocity should flow from higher potential to lower potential, right? So phi x should be greater than phi y. Okay, so now the potential lines are radial lines and the stream lines are circles. So what you will notice is that even though we have an irrotational flow, we can define a vortex. Now what is the problem? Why is this not realistic? This is not realistic because it's an incompressible irrotational flow. We have not assumed any effects of viscosity. So that means a vortex should not exist. And still we are able to define an irrotational vortex. So the reason is, if you look at this equation, psi, or just look at Vr and V theta. V theta at r equal to 0. At r equal to 0 means at the center. At the center you have infinite velocity, and this is not possible in reality. That is why these are called ideal flows, ideal elementary flows, where you are basically constructing a flow which is an approximation, and this approximation is fine as long as you are far away from the origin. But if you are going to be closer to the origin, this approximation is not good. And in fact, irrotational vortices are used in many simulations or to solve many types of flows. But we always remember that there is this condition, there is a singularity, that velocity is infinite at the center, and this is not okay. And why does this singularity happen? It is because you have not taken into account the effects of viscosity. Is this part clear? Yeah. Okay. So I have one more interesting flow. Actually, there are many, but I just want to discuss one of these interesting flows. Now, what we can do is, we have studied some elementary flows. We can take a combination of these elementary flows and we'll get some interesting phenomena. So for example, if I take, so we have defined a source, a sink, uniform flow and a rotational vortex. There is also one more thing which let me define, which is called a doublet. And a doublet is when we have some velocity Vr which goes like cos theta with a dependence on radius also, minus lambda by r square. I'm not going to derive this in detail, but I'll just show you how the flow looks like. And V theta is again minus lambda by r square into sine theta. And if you can take this as an exercise, if you try to define psi and phi, so psi turns out to be minus lambda by r sine theta, and phi turns out to be minus lambda by r cos theta. Okay, and how the flow looks like is this. So there is basically both a source and sink at the same point. So on the right side, what you will see is that the flow is trying to go towards this point, and on the left side you'll see that it is trying to go away. So you imagine that you took a source, okay, you have A, which is a source, and you have B, which is a sink, and you bring them very close to each other. Okay, so this is how the flow will look like. So on this side, this is opposite. So on this side, you see the flow is trying to come towards the point, but on this side, the flow is trying to go away from the point. And then somewhere in between, it will have to rotate. So it will rotate and come like this. Okay, so this is called a doublet. This is something we can imagine and define like this, right? So there is this kind of a flow, and from here the velocity field goes like this. Okay. So let us take one example where we combine these elementary flows, and you'll see why it is so helpful to define these elementary flows. So combine elementary flows. Okay, so let's start with a simple thing. I'm going to take a source plus I'm going to take a uniform flow. Okay. And let me start with analyzing the stream functions. I'll not take the velocity. See, stream function is a scalar. So I can simply add. I can say psi of source plus psi of the uniform flow I can just add, and this is my new psi. So what was the psi of source? So let's go back. For source it was, so we just derived it here. Yeah, psi is q theta by 2 pi. So let me write this. Q theta by 2 pi plus the uniform flow was, we had a constant velocity u, so we just had u naught into y. Okay, and then there can be some constant. So this is my new psi. Given this stream function, now what is my velocity? So that we can define. Let's also write phi. Again, phi nu will be phi source plus phi uniform. So phi source plus phi uniform is phi nu. And so this is minus u naught x, if I remember correctly. Yeah, and the potential function for a source was, yeah, minus q by 2 pi log r. So I'm going to write that here. Now the problem is we have this in r theta coordinates and this I have in xy coordinates, right? So I'll have to convert into one of the coordinate systems. So let's convert to r theta because we know the relation. Okay, so I'm going to write y as r sine theta. Okay, so this we know, and x is r cos theta. So similarly I'm going to write here r cos theta. Any questions still here? Why we are doing this? So now you imagine that there is a source sitting over here, but there is uniform flow here. So if this is the source, velocity was flowing like this, but here there is also a flow coming in this direction. So what will happen at this point is that there will be interaction at some point, and the flow which is coming like this will actually turn this flow around, and there will be a turning motion because of the interaction. And you'll see that the velocity field is actually something like this. So this is the flow. And inside also there will be some funny flow, like for example there is velocity vectors in this direction. If you try to solve for these equations and you plot, you can do this on a computer, so this is what you will get. But instead what you can do is just forget what was here and consider this as a hatched region. What you have obtained by simply adding a source and uniform flow is flow past a bluff body, which is a very realistic flow, right? So you see, you took a imaginary case where you have a source and a uniform flow. Source, we know it's realistically not possible, and still we define it. Why? Because of this reason. Because when I take combination of these elementary flows, I can produce more complex flows which are useful on a regular daily basis or in a real world. Okay, so this is flow past a bluff body. Any questions on this? In fact this is called half bluff body, because this body seems to continue into this direction, right? So this keeps continuing in this direction, so it is called a half body. You can actually produce a full bluff body. So let's take a second case. So this time we'll take a source and we'll take a sink and we'll take uniform flow. So let me not write the stream functions, that's not needed, but you can just imagine by drawing the velocity field, you can imagine what is going to happen. So this is, let's say, source, and it is placed at some distance with the sink. So of course the velocity that's coming out will go into the sink, right? So eventually it will turn and it will go into the sink. But now you have also added on to this a uniform flow. So what happened in the first case? Because of this interaction, there was this boundary, kind of a boundary created, right? So similarly, kind of a boundary will be created here, and a kind of boundary will be created on this side, right? Because uniform flow is supposed to go like this, but there is also a sink which is sucking in the velocity, right? So there will be a boundary created over here. Within this boundary, everything goes into the sink, and outside this boundary, the flow will be of this type. Similarly here, within this boundary, the flow is coming out like this, but beyond this side, the flow is actually moving like this. Okay, so if you combine this now and redraw this, so you have a source, you have a sink, and you have a boundary which is created. Within this, what happens is the flow goes like this. Okay, and outside the flow is, it is uniform, but it turns around this body and then again becomes uniform. Okay, so now you see that there is a full body which is created. This is actually called the Rankine full bluff body, which you were able to create by simply adding 3 elementary flows: source, sink, and uniform flow. Okay, and there are many more examples, like you can take a vortex and you can take a uniform flow, and that will give you something different. If you take a, so this is again something which is done. So if you take a doublet, which we defined in the end, and then you add a uniform flow, it will give you flow past a circle or a circular cylinder, and this is a widely studied phenomenon. So flow past circular cylinder. So if you take an advanced course on fluid mechanics, you will actually have to solve all these cases. Any questions here? Any comments on what we just did, combining the elementary flows? One last example which may be of interest. If you take a source and a vortex, what do you think will happen? Or sink and vortex? See, vortex is, irrotational vortex is what? There is some circular motion, and source is radial motion. If you have both radial and circular motion, it becomes a spiral. Okay, so you get a spiral vortex. So you can in fact try and draw the velocity fields as an exercise. So I'll stop here. If there are any questions on whatever we have discussed, you can ask. Okay. Otherwise, we can stop for today. Thank you, everyone.